stimulus, diversification, and coverage closure of 3D NAND flash with artificial intelligence. Asterisk, given the ever-increasing complexity of 3D NAND flash designs, the tighter tape-out timelines, applying the machine learning ML algorithms in the pre-silicon design verification (DV) has become essential to ensure the satisfactory coverage within the project schedule. This work proposes the using the reinforcement learning RL algorithms that use several deep neural networks DNA coupled the gradient-ascent approach to determine the desired stimulus setting that cover the highest number of the unit coverage beams. A feedback loop is established to train the model from the coverage database to the RL agent and from the RL agent to stimulus generation. The RL agent is trained in several iterations without the actual design under verification DUV, and the trained model is later used in the actual DUV to generate the best stimulus that can reach the highest coverage. Chapter 1 is Introduction. Verifying the 3D NAND flash NAND full chip functionality by meeting coverage goals is required for design tape-out. With rapidly increasing NAND design complexity driven by the high performance demands and diverse requirements, achieving a coverage goals before tape-out becomes a severe change to the design verification team. This paper uses machine learning ML techniques to generate stimulus and loop settings, aiming to achieve optimal verification coverage. With a significantly reduced number of verification cycles, some specialized category of the ML algorithms such as reinforcement learning RL and multi-armed bandit algorithms and gradient-ascent approach and advanced neural net architectures are used to identify optimal setting of the stimuli to maximize the coverage with minimal manual intervention. This work aims for a faster coverage closure, giving more time to the DV team, further expanding the scope of verification. Chapter 2. Existing design verification environment. 3D NAND Flash DV team follow the industry standard coverage-driven control random verification methodology to verify the NAND designs. DV flow the start of the retrieving and understanding the VIN and NAND design specification documents and planning for the verification. Later, separate verification plans are left for each new NAND feature. Sequences as a function of coverage and behavior white box checks are developed in a SystemVerilog SV independently per the verification plan. After the test bench development, the DV team runs regressions and debug failures and analysis coverage gaps using the coverage report that are generated by the simulator tool. This cycle repeats till satisfactory coverage goals are reached. Figure 1 illustrates this process. The part highlighted in the green will be explained in a later section. Figure 1. Machine learning in DV flow. The functional coverage is a key metric to measure the verification and is widely used across the industry to sign off the verification with confidence. Functional coverage is a collection of cover points that are grouped into cover groups by their relevance. Each cover point is mutually written by the DV engineers to represent each future operation of the state of the NAND. Many cover points are often close together to cover valid feature, register, or operation combinations. Coverage bins count grow exponentially when cover points are close together, resulting in an exceedingly high number of bins to be covered before sign-off. The current NAND TV has around 500 kilo bins that need to be covered by random sequence generation. For highest confidence coverage accumulated throughout the verification cycle is set to 0 for final tape-out netlist, which makes closing coverage more challenging. So the current test bench issues random operation in random order to NAND by enabling random configuration to cover a wide range of command, address, data, and feature requirements. Randomization in SystemVerilog is enormous powerful that is often used to be controlled by writing constraint to direct the randomization. Sequences are developed to have nodes SV parameters control the stimulus by steering random SV constraint without modifying the sequences or test. The detail of these nodes will be discussed in later section. There are several hundred of knobs in the current to adjust the values of these knobs and run targeted regulations to fill coverage holes. Consider the indirect or direct relationship between the nodes can nullify each other impact and the complex correlation of the nodes to the coverage beams. This is a very tedious and arduous process. These activities can sometimes yield an undesirable result, meaning that the target beams are not hit even with the multiple targeted regression. This process can often take multiple weeks to fully coverage and account 10 to 20% of the entire verification cycle. Chapter 3 is the proposed model. A reinforced learning RL agent that uses a deep neural network DNN is incorporated into existing DB infrastructure, highlighted in green in Figure 1. Reinforcement learning is a specialized category of the machine learning algorithms which aims to maximize the reward by continuously modeling and optimizing the mathematical relationship between the input and the reward. RL algorithms can be leveraged in the current DB flow to accurately model the relationship between the knobs and that are used to generate a stimuli to maximize the reward, which is the coverage score. A framework is developed to integrate the RL agent into existing test coverage flow independent of the design under verification DUV, building a feedback loop from the coverage database to input knobs via RL. Our RL agent will use coverage report to find correlation and relationships from input knobs to the reverse as well as correlation between the input knobs. Then RL agent aims to produce an optimal new set of the knobs that can maximize the coverage score. There are 4 key requirements to accomplish this: visual stimulus controlling knobs, a block box model of the UV, black box or block box. As a feedback path from the coverage database RL agent and an RL agent. Feedback path from coverage database to RL agent and on RL agent. Okay. The RL agent aims to produce an optimal value for each of the knobs, which collectively can maximize the coverage score. So it's essential to the TB random sequence generation is controllable by the external nodes. There are several concepts such as SystemVerilog parameters, command line test, $test, $plus R, or the UV and command line processors can be leveraged for controlling the stimulus generation either from a command line or by modifying the global parameters file. An example of a SV distribution weighted constraint and parameters is shown in Figure 2 to illustrate how nodes control stimulus. Here, SV parameters, both XEN, both YEN, and both GEN can control the random variables mode. If the mode X targeted for coverage, both YEN, both GEN can be changed to 0 so that the mode will always take both X as desires. After RL agent generated the node values, on automation is required to update node values in the TB and start simulations. In this example, the parameters can be moved to a global parameters file which can be updated automatically. As described in section 2, Micron NAND testbench is developed systematically to have these constraint controlling parameters in global file which is uploaded automatically after RL agent generated new knob settings. Figure 2, an example to knobs controlling the stimulus. As TB is changing rapidly throughout the verification cycles, RL agent need to be trained periodically to accommodate newly added nodes and coverage bin, so that a typical RL agent is trained in several iterations, with each iteration involving hundreds of design simulations. This can extremely delay the training process as the design simulations are slow in general. So the process of the learning correlation from the stimulus to coverage bins is decided to the test bench environment, which is independent from the actual DV. So it is highly recommended that the actual DV be removed from this process. A black box model of a box functional model BFM mimicking the behavior of DUV can be used to replace the actual DUV. So this would also save costs related to the using computational resources and simulation licenses that actual DUV requires. The final requirement in the DV environment is to establish a feedback path from coverage database to the RL agent. Any industry standard simulator can generate coverage report per simulation in text and HTML format. An automation is required to be developed to parse the coverage report, extract the coverage score, and pass this information back to RL agent in a tabular format. Before sending the coverage data to the RL agent, extract the coverage scores are mapped to the node settings with their associated. An example table of knobs and a coverage score that is fed back to the RL agent is shown figure 3. So the figure 3 is an example table of knobs and coverage scores. So the reward to the RL agent is customized to be either the absolute coverage score or the relative coverage score with respect to the already hit coverage. So using knobs as an input. So RL agent can be more effective when reverses the relatively coverage since it aims to increase the newly hit bin count. So while developing cover point, they are grouped into cover groups based on their relevance for each feature, operation, or algorithm. Independent RL agents can be trained parallelly to improve each cover group by changing the reward from total average coverage score to a particular cover group score. These feature-specific trained models can be extremely important to reach newly introduced feature coverage goals to ensure the highest design quality. To maximize the risk of a potential over-reliance on artificial intelligence in the proposed DV model, reward should be customized and controlled very carefully by DV engineers. So additionally, DV engineers should review the training knob settings and coverage scores before using them on real DV. Authors think that the chances of complete failure of artificial intelligence is nearly zero with careful human involvement at each necessary step into the process. In the worst case of the complete failure of this approach, RL agent would have at least produced a unique combination of knob setting than traditional manual settings. That may uncover corner design bugs with less overall coverage improvement. Chapter 4 is reinforcement learning agent. The RL agent used for this work is developed by the VerifAI Incorporation. Reinforcement learning is a technique in which an agent takes action in an environment. The environment returns a reward and a representation of the state of the environment to the agent. So the agent takes the next action in the environment based on the reward and the state of the environment. In applying reinforcement learning to the design verification problem, the environment is DV environment and the reward is typically coverage. The RL agent can be a deep neural network, DNN, that learns to take the best actions based on the reward. RL agent used for this work utilizes advanced RL and robust optimization algorithms such as gradient-ascent approach that and this perturbation techniques. It also employs sophisticated neural network architectures using wide networks with batch normalization and leaky ReLU, leaky rectified linear unit networks. So that the error agent is given an optimization problems where we have the set of the input features X, input nodes, which may constrain the relations between them. If they represent relative weights, the input nodes can be continuous within a range or have an enumerated type that just have values from a list of possible values. Our agent is configured with the output labels columns representing the objective metric we want to optimize. To use the reinforced terminology, we can call this reward. The RL agent first fits a DNN that has enough capacity to capture the relationship between input nodes and the output metric. Then it uses the gradient-ascent, the output of the DNN Y, with respect to the input features X to find the best node settings that maximize the output of the DNN subject to constraint defined by the penalty term. A sample gradient-ascent functions is plotted in figure 4. Figure 4 is simple gradient-ascent surface. The fundamental idea behind the gradient ascent is to update the parameters of the variables iteratively in the direction of the deepest climb of the function. The updated rule for the parameters at each operation can be represented as in where the 0 represents the parameters of the function f that we want to maximize. Eta is the learning rate, a positive scalar determining the size of steps to take in the direction of the gradient. Delta f theta is the gradient of the function f at theta, which points in the direction of the swiftest ascent. Theta new equals theta old plus eta delta f theta. The gradient ascent process starts with the initial set of the parameters theta 0. Later gradient delta f theta t is evaluated at the current parameters values. In the next step, the parameters are adjusted in the direction of the gradient to move forward to the maxima as shown in figure 2. This process is repeated until the changes are sufficiently small or the maximum number of iterations is reached. This can be also include a condition like a gradient being close to 0, indicating a potential maximum. This process is illustrated in figure 5. Theta t plus 1 equals theta t plus eta delta f theta t. Figure 5 is sending a function along with the gradient. The loss of function used to the gradient ascent technique as a penalty can be expressed as 3, where fx is the function being maximized, the modeled prediction. Px is the penalty function when I compute the penalty based on how far x deviated from the desired constraint. The lambda is a penalty weight, a scaling factor that determines the frequency of the penalty term relative to the predictive term. Lx equals minus fx plus lambda px. The negative signs of before the fx is being maximized. The loss L used in a gradient calculation is technically being minimized. A common approach on the optimization algorithms. The penalty function at px could be structured in many ways depending on the constraint. For example, if we want the sum of the certain variables in x to equal 1, a common constraint probability distribution or normalized settings. Px might be the defined as 4, where px penalized the main deviation of the sum of the component of the x from 1. Scaling the difference to ensure the penalty is always positive and more pronounced for larger deviations. Px, the summation I equals I from 1 to n, the xi minus 1 the square. The process of the RL agent starts with the random plausible settings for input node X. It is iteratively adjusted the setting using the gradient of the DNN output Y with respect to the input, which includes the penalties for constraint violation. So the RL agent attempts to maximize the network out by adjusting the node based on the compute gradient. Optimal settings send a corresponding network out after the specified number of iterations. Chapter 5 is RL agent training. Before the training starts, the RL agent is configured with the testbench node type and range of each node. This RL-based model is trained in n iterations. Each iteration begins with the model generating R unique node set, with each node set as number of the NAND simulations are run on the NAND model, and the coverage accumulated per node set. That each node set is ranked based on how diverse the stimulus is, that is, how many unreachable beams that can hit. This ranking is completely customized based on the end goal, which is coverage closure in this case, and this is what will be fed back to the agent as a reward. In each iteration, RL agent builds and optimizes neural networks to understand and model the relationship between input nodes and output reward. The agent then generates the next node set, which aim for further improve the reward. After all the iterations are finished, our last iteration is not necessarily the one the highest coverage due to the RL agent being not fully trained, or RL agent is learning negative correlations. So the best node set that have highest coverage among the n iterations are handpicked to run regressions with the actual DV. This training process is illustrated in Figure 6. So that is Figure 6 is the RL agent training process. Chapter 6 is results and future works. Figure 7 shows the coverage plot from one of the ongoing proof of concept project training iteration. This plot illustrates the improvement that this work has made. Figure 7 is a comparison coverage lamp. With the ML methodology, a higher coverage of 2% can be reached with the same number of 10,000 simulation, and the same amount of existing coverage can be achieved at 80% fewer simulations. Given the manual effort spent, these results are very encouraging in pursuing AI/ML to improve design verification. Additionally, this increased coverage trajectory and reduced simulation time gives the verification time more to further improve verification to find more design bugs. In this work, there is more room to fine-tuning rewards and finding the correct balance between R, number of unique node sets, and S, number of seeds run per unique node set to maximize the coverage. More experiments are being run by adjusting reward metric using different combination of R and S, and by using more advanced RL algorithms to reduce the training iteration and improve the coverage further. Chapter 7, Conclusion. An automated RL agent framework has been developed and incorporated into existing PB flow. RL agent aims to generate an optimal node setting to steer the random stimulus generation to reach maximum verification coverage. RL agent will be trained in DUV model and or DBFM iteratively throughout the project cycle to learn the effect of each node on the coverage score and on other nodes. Later, trained RL agent is used on a real DUV to cover the highest number of unique coverage bins in the least simulation possible. Results of this work on proof of concept project are promising, and we see an opportunity to deploy it for future NAND products to aid the DV team improving the stimulus and closing the coverage. Efforts will continue to further fine-tuning the model, improve the result, and potentially expand its use on verification of future NAND products. Okay, today I read this paper, the stimulus diversification and coverage closure of 3D NAND flash with artificial intelligence from DVCON2025. Thank you for your time. See you next time.